Hello everyone, my name is Daniel and today we're going to talk about LeFlow, enabling flexible FPGA high-level synthesis of TensorFlow deep neural networks. This is a work developed by me and Professor Steve Wilton at the University of British Columbia in Vancouver, BC. Before going to the demo, I'm going to talk about the definition of the problem being solved, and then we have two things happening in parallel. First, high-level synthesis are emerging as a promising productivity booster, and many companies such as Intel and Xilinx are heavily investing in those tools. Efforts are being put to enable software designers to program hardware, but we are not quite there yet. At the same time, deep learning has gained increased attention. Modern frameworks are allowing abstraction of implementation details, and those same frameworks also allow non-experts to experiment with state-of-the-art DNNs. Nevertheless, modern HLS tools are still far from high-level machine learning frameworks, and non-experts in machine learning are faced with complex implementation details when using HLS tools. To allow broader FPGA adoption in the machine learning community, a higher level of abstraction is needed. So the key idea of this work is to enable TensorFlow hardware synthesis using LegUp. TensorFlow is an open source library for numerical computation using data flow graphs. It has extensive support for deep learning algorithms, and XLA was also recently introduced. XLA is a domain-specific compiler for linear algebra that optimizes TensorFlow computations. On the other hand, we have LegUp. LegUp is an open source HLS tool being developed at the University of Toronto, and it can synthesize most of the C language to hardware. A normal LegUp flow looks like this. First, a C program is fed to a C compiler, and then optimized LLVM IR is generated. When this information is combined with the target hardware and user constraints, we're able to perform allocation, scheduling, byting, and RTL generation, resulting in synthesizable Verilog. Our flow does not use a C program, but it actually uses a Python program. This Python program is then fed to TensorFlow. TensorFlow uses XLA in its backend, and it creates optimized LLVM IR for us. This LLVM IR is then fed to our tool, which is LeFlow. LeFlow restructures this code and sends this code back to LegUp HLS, resulting in synthesizable Verilog. This promotes easy hardware generation. It's a minimally intrusive solution since there is no need to modify TensorFlow or LegUp, and is also more flexible than related work that are based on other frameworks or only have a couple of kernels implemented. So let me make a very quick demo here for this. So let's start with my simple MLP, which is a simple multilayer perceptron with 784 inputs, 10 outputs, and also a softmax. In order to run this here in hardware, in order to run this in the CPU, this is what you would normally do. In order to run this here in an FPGA, you just simply call LeFlow mysimplemlp.py, and this will generate a folder here called mysimplemlp. And if we inspect this folder and go all the way to the end, we will see mysimplemlp.v, which is a Verilog file containing all the hardware description language. So it's a hardware description language for this specific example. I can also give you a more simple example, which is a max pooling 2D. So in this example here, we're actually using a real data set, which is the MNIST data set, and we are doing a max pooling of 3x3 with strides of 3. So again, in order to run this, I simply run LeFlow mymaxpool.py, and this is gonna generate first an image, so this image that's being plotted here, and this is gonna generate hardware for us. So the Verilog file can be found here, and if I run makev, which is model sim, I can actually come up with some outputs for this. This is going to be dumped here, memory dump.txt, and with the simple script, I'm actually able to read and plot this output, which we can see here, so we can actually see that our tool was performing correctly. I'm also able to synthesize this here using Quartus and inspect the hardware as you can see it here. So we can actually see that we have a input memory, have an output memory, so things are being generated properly, and we can also have a look at the final state machine if necessary. So for our demo, the idea is to demonstrate how easy it is to generate deep neural networks using our framework. So users will be able to change TensorFlow algorithms based on many available templates that we have, and test the result of the HDL in seconds using ModelSim. We'll also make a demonstration of functionality with the algorithm running an FPGA. So a trained neural network will be performing inference on an FPGA, and the user will be able to choose the input and inspect the results through Xilinx Memory Content Editor. Thank you very much.